Okay, great. Okay, guys, so today we are covering the Wkb approximation. And in a way, this is the end of quantum mechanics. This is kind of it, because next week and the weeks after, we're really going to quantum field theory. Not directly, but we are beginning the seeds of quantum field theory by covering the path integral formulation of quantum mechanics. I'm very, very excited to teach you guys quantum field theory because that's my daily language. Now today, the lecture is kind of light. I'm going to kind of show you what the Wkb approximation is. We'll derive it. You'll derive it again on the homework. I kind of want to show you how it works. It's important. You'll use it, and then we'll move on. I'm not going to spend too much time on it doing a ton of problems with it because it's sort of one of those things that when you need to use it, it's very straightforward, and you just use it and you move on. If you take quantum mechanics in college, if you become physicists, then you'll do all the problems you have to do with it. But for our purposes, I'm not so crazy, gonna go so crazy with it, but I will derive it for you today. After that, since Gabe is not doing a problem solving session, I thought I would do something very special and very slow and very different. So I've taught a lot of different classes for the public, for high schoolers, for college students. I even taught a class. I even did a seminar with graduate students one time on the research I was doing, which was weird as an undergrad. Everyone kind of chuckles when you walk in, but I taught a class for the Science Honor Society at my high school titled The Conceptual Basis of Quantum Mechanics. And what it showed some mathematics, but it was a class to really tell you what the heck is going on with quantum mechanics. Like, what are we doing here? I think that's what I'm going to do. I'm going to give that lecture after I do the Wkb approximation. And for all of you, it will be a very good sort of pause, relaxing, not a lot of math, not a lot of algebra, just to realize, like, where have we gotten to and what do we know so far? Just to kind of get your feet firm in the ground. Not a lot of math, not too complicated. I will make it a little more mathy because you guys know so much, but I think that will be very useful for all of you. And I want you guys to ask a lot of questions when we do that. And we might go a bit over 11 just to, because Gabe's not here. So I figured I'd use that time wisely. Now, a part of that, the motivation for that lecture titled The Conceptual Basis of Quantum Mechanics was classical mechanics. So I used some classical mechanics, which is something that everyone knows, presumably from high school, to motivate the quantum mechanics, to sort of motivate our discussion of the quantum mechanics. And so that's what I'll do now. And I'll actually show you a very important tool that we need for quantum field theory. And so that was a talk I gave that sort of helped people, because it's very easy to get lost in mathematics. And that's not good. You don't want to be too lost, because if you're just reading equations, but you don't really know what's going on, that's not really good. Because as a physicist, as a scientist, as someone who really wants to master a subject, you should be able to break it down into some very basic, like a checklist. That's what I'm going to do for you today, okay? Because I think it will be a good stopping point before we go to the path integral, which is very mathematical. And the path integral is going to take us probably the next 3 or 4 weeks to really understand. And then by then, we'll be at your final presentations and final papers. So all we're doing for the rest of QM is the path integral, and that will take us into field theory nicely. Okay, any questions from last time or from anything else? Gabe mentioned to me, Olha, that he will send me the problem set answers. So I'm waiting on them, so. Okay, let's begin. Let's do the Wkb approximation. So WKB actually stands for the names of 3 scientists. I have them written down today. Their names are Wenzel, Krauss, and Brillouin. Who knows? It's actually spelled, okay, this is, someone else came in. It's fine. For the person who just came in, after the lecture today, I'm giving a very brief overview of everything we've covered. So if you haven't shown up to anything, this is the perfect lecture to come to. You'll feel like you know all of quantum mechanics, okay, which is good. So actually, the Wkb approximation is called different things in different parts of the world. So this is funny. I had no idea. I was reading a paper the other day and they said, we will now use the Kwb approximation. You go, what? What is that? And it's the Wkb approximation. They just label the letters differently. So if you're reading something and it's confusing, know that in different parts of the world, I guess they think different scientists were more important. But anyways, let's begin. It is another approximation method. We're starting to notice a trend here. We love approximation methods, right? We did perturbation theory. That's approximation scheme. In the hydrogen atom, we did another approximation scheme, right? With that asymptotic peeling off of our differential equations. And now we're going to do yet another approximation scheme that's very useful in a lot of contexts. So let's derive this Wkb formula or approximation. So let's start with the time-dependent Schrodinger equation. I should write these as partials. I'm so used to not writing them. Actually, I should write this the right way, actually, because
could you pin your screen, please?
Sorry?
Could you pin the screen?
Oh, yes, yes. Thank you. Thank you for pointing that out because oh gosh. Spotlight. Is it good now?
Yeah. Thanks.
Yeah, no, thank you for pointing that out because last time it was really crazy. It was like moving back and forth. Thank you. Okay, great. Okay, so we start with our normal time-dependent Schrodinger equation. Right, so this is our standard thing. I've gotten so used to writing the time-dependent Schrodinger equation that I forgot how to write the time-dependent one, but here it is in all its glory. Okay, and I'm just going to rewrite this in this way. D2 psi x squared plus v psi equals e psi, right? And this thing is our Hamiltonian, which we know. I'm going to go very slow with algebra today. So I'm going to do this derivation super slowly, okay? Because I think it worked last time. I feel like people got it more when I went a little slow and didn't say, oh, this is easy to get. Just do all the algebra yourself. No, we'll do the algebra today. I'll derive it for you today. I'll derive it with you. Now I'm going to do some things to this to put this in a very interesting form, and you'll see what I mean. First thing I'm going to do is do some algebra. So let's move this potential over. D2 psi dx squared equals e psi minus, I'm going to write this as a function of x. Okay, I just move that over. I'm going to go slow. Now I'll move this fraction over, minus h bar squared over 2m. So what do I get? I get d2 psi over dx squared equals what? 2m times e psi minus v of x psi over h bar squared, and I can't forget that minus sign when I move the fraction over. Good? That minus sign is there. Okay, now I'm going to pull out a psi, okay, and I'm going to write this in a very interesting form. So I have d2 psi dx squared equals psi e minus v of x times 2m over h bar squared, and don't forget that minus sign, okay? And if you recall, for the free particle, the energy of the free particle is E equals p squared over 2m, right? This is the energy of the free particle we've seen, which means that the momentum p squared equals e times 2m, right? Which means that the momentum equals the square root of e times 2m. Okay, this is kind of interesting. I kind of have this form here, right? Because E minus V is just my energy, right? It's whatever's left over, right? E is the total minus the potential is going to give me some energy that's left over. So I can kind of rewrite this in the following way. So I'm going to rename a variable. I'm going to call P the following thing, right? I'm going to call P, what should I call P? Yeah, I'll call P the square root of 2m times E minus V of x. Okay, then what does this equation become? My Schrodinger equation becomes d2 psi dx squared equals minus p squared over h bar squared psi. Okay, this is kind of an interesting form to put it in because now we're working with some kind of momentum. And really, when I say we're working with some kind of momentum, we're working with some kind of velocity, right? Working with some kind of velocity, right? Because you know from high school, just as a quick reminder, P equals mv, or P equals mx dot in our physicist notation. Okay, does all this make sense? How I've gotten to this form? Usually, if I'm teaching you guys, I just throw up the form, I get it in, and I say, that's it. And this is how I label. And I leave you to figure out all the algebra. But I'll take an extra minute today, and I'll do all the steps. Good? Okay. Okay, so now I have my time-dependent Schrodinger equation in kind of an interesting form. And this is the form I'm going to play around with now. Okay. Okay, cool. So let's continue. I can erase, right? Okay, you're going to have to, okay, good. Oha made her head nod more vigorous. You have to make it more vigorous, otherwise I can't see. Okay, so, you know, if you're doing a project, you're kind of playing around with this equation and you go, oh, this is kind of an interesting form because it gives me something like a momentum. This is kind of interesting, right? Some P of X, right? This is weird. Now, what can I do with this? So let's think about it. I'll wait for Olha for the go-ahead to erase the board. Take your time.
I have a question. I kind of
sure.
didn't get how you went to the equation from the in the top from the one that you highlighted, like that step.
Yes, anything in particular?
I mean, how did you move to on the other part?
Which one?
Like lower.
Here?
Next step.
Here?
No, on the left.
This?
Lower.
This?
Yeah.
Okay. All I did was I moved this fraction, this over. So I had to divide by h bar squared and I had to multiply by 2m. That's it. Right, because these two terms are multiplied. So if I wanted to put this term on the other side, I just had to do, right? So this is dividing, so I had to multiply it over. This is up top, the numerator, so I had to divide it.
Yeah, but where did it disappear on the left near psi e?
What
Lower.
disappeared?
Yeah, here.
Yeah. Oh, yeah. Oh, right. Good. I pulled out the psi. Good.
Oh, okay. Thank you.
Yeah, sorry. Yeah, I pulled it out. There's not one side, right? Because that's how I end up with this psi out here at the end. Okay. Yeah. Okay, good? Okay, can we move on? Okay, good. Okay, so now I have my time-dependent Schrodinger equation in kind of a nice form. Let's play around with it. Let's see what we can do. Beautiful. Okay, now let's think about what psi could be and compute the derivatives of psi, right? So what is the most general way I can describe psi? That's what we should think about. We know that we can describe psi as plane waves, right? So one way we can describe psi is just psi of x, forget about time dependence, equals e to the I kx, right? Where k is our usual wave number, 2me root over h bar, right? So this is our like standard way. It's just a plane wave. But there's an even more general way we can describe psi. The most general way we can describe psi of x, forget about time dependence. I don't care, even though I have, notice how I kind of took out the time dependence here. It kind of disappeared. So I don't really care about time dependence. So I have psi of x equals a of x e to the I phi of x. This is the most general way I can write the wave function as some amplitude, right? So what is the amplitude? Amplitude is the height of the wave, okay? And phi is the phase of the wave, right? So not the frequency exactly, but sort of how much I'm stretching it or compressing it, or how many periods I'm putting into one interval. So this is the most general way I can write the wave function as some amplitude and some phase. And we saw phases in the first lecture, right? When we treated psi as a vector, which it is, in a complex plane, and we moved it around the complex vector field. So now a is a function of x and phi is a function of x. Does this make sense? So this is what we are going to work with. And sometimes you'll see the Wkb approximation called the phase integral approximation. Okay, that's what you'll see it called, because we're dealing, the idea is, can we write the wave function, or can we describe the wave function, or can we write the wave function really as just its phase, just describing it by its phase, which is useful in a lot of circumstances as an approximation. I saw someone's mic unmute and then they muted again. Did someone have a question? Okay. Okay, good. So let's work with this. Let's do some derivatives on this thing, okay? Let's see who remembers their derivative scales. So let's do d psi dx, okay? So let's do d psi dx of this thing. So d psi dx of a of x e to the I phi of x is what? So we're going to need two differentiate. I'm going to go super slow in case people are not comfortable with derivatives. We're going to need two rules here, right? I'm differentiating with respect to x. So I'm going to care about my a, that's a function of x, and I'm going to care about my e to the I phi. I'm going to need two rules to differentiate this thing. I'm going to need the product rule, right? Because I have two things multiply. And I'm going to need the chain rule. The chain rule because of this exponential. So let's use the product rule first. What is the product rule? Product rule is really simple. If I have d dx of two functions, a of x and times b of x, the derivative goes as follows. You differentiate the first thing, and I'm just going to do this. I'm rewriting it in this way because I want to make sure you know it's implicit that these are functions of x. Because I'm going to drop these x's, okay, in a second, because this is going to get long. So I'm doing this, and implicitly you should know these are functions of x. So what is the product rule? I take the derivative of the first thing, subtract, leave the first one alone, take the derivative of the second thing. Okay, that's the product rule. Very simple.
Add.
Yeah.
The product rule.
Sorry?
Don't you add the two terms in the product rule?
Okay, you add them. There you go. Usually I forget, and then at the end I check to see if my answer makes sense, and I change the signs. Thank you. See, it's been a while since I took a calculus class. I trust Rika for differentiation rules. Okay, fine. So let's do that. So I have a of x. Let me differentiate that thing first. I'm going to get a prime. I'm dropping the x's, and I'm going to leave the e to the I phi alone. These are implicitly functions of x. Oh, prime. A prime denotes, so a prime just means I took a derivative, a spatial derivative, dA dx. If I used a dot, this is physicist notation, this refers to a time derivative. Okay, just for notation. So this is not a time derivative. That's why I'm not using dots. I don't want to abuse the physicist notation. Okay. Okay, fine. Okay, that's my first term. Now, thank you, Rika, for correcting me. I need a plus. I would have been a minus. And now I'm going to differentiate this piece, right? I already got this piece, so I might as well just put it there. How do I do this thing? I'm going to need something called the chain rule. What's the chain rule? So if I have something e to the alpha x, I'm not going to give you a lecture on the chain rule. Just going to show you how it works with exponentials. If I take the derivative d dx of this thing, okay? Let's call this little piece, this is a function, right? Inside this exponential. I'm going to call this little piece rho, okay? So what the chain rule tells me is this derivative is equal to rho prime e to the alpha x, right? Because the derivative of an exponential is just itself. Okay, so what is rho prime? Rho prime is just alpha, right? Right? This x just drops. So the derivative of this thing is just alpha e to the alpha x. It's just pulling down a factor of x. Now, if this was e to the alpha x cubed minus x squared plus 2x, something like that, it's not just going to pull out a factor of alpha. It's going to pull out other things, right? Because you're actually differentiating this top piece. Okay, fine. Let's just do the second derivative for kicks. So if I wanted to do the chain rule twice on this exponential, I would get alpha squared e to the alpha x, right? Because what is this really equal to? It's literally, I'm taking the derivative twice, right? Literally, back to back. It hits it, then it hits it again. Okay? Okay, great. I just taught you calculus 1. You can thank me later. That's my lecture on the chain rule. Now we move on. Okay, so now what am I going to get when I differentiate this piece? Well, I'm going to get a factor of I pulled down, right? I'm going to get this phi prime, right? Because I don't know if that's a constant, so I can't ignore it. And I'm going to get back my original thing, e to the I phi. Cool? There we go. We just did this derivative. Now, usually if I was teaching you, I just write down the derivative and say, there it is, guys. Do it yourself. But I said, let me go a little slow today because I don't have much to cover. Okay. Now what do we need in Schrodinger? We need the second derivative. And this partial doesn't really matter because I'm still only looking at x dependence, right? I'm not looking at y or z dependence. So this is kind of silly, but it's fine. Let's do the second derivative. Oh, this is going to get kind of nasty because now what this really means, I already have the first derivative of psi. So here's the second derivative. I have to just differentiate this thing. So I'm going to get a lot of terms here. Okay, so let's differentiate this first term first. Okay, we'll call this term alpha and we'll call this term beta, just so it's clear. So let's differentiate alpha. So alpha equals, or it goes to, d dx of a prime e to the I phi. Well, this is really easy to do, right? Now that we broke it down. Differentiating the first part, now I get a double prime, two derivatives, right? My e to the I phi stays the same. Again, thanks to Rika, I know I have to add. I get a factor of I down, so this a prime stays alone, and I get a factor of phi prime. Okay? That's alpha. Now let's compute beta, which is d dx of a I phi prime e to the I phi. This looks a little bit more complicated. Now I just have three things I need to do. Three terms I need to differentiate, okay, in sequence. So first I differentiate a. I get a prime. This was a bad way. I shouldn't have even labeled them. I should have done it all at once because it's not that bad. I don't know why I thought it was going to be way worse. Let me just do it in one line. Okay, so I get a double prime e to the I phi plus a prime I phi prime e to the I phi. Okay, now we're differentiating this term. So I differentiate this thing, right? A prime I. So everything else stays the same, right? So I took care of the A. Now I got to take care of the phi prime. Rika, when I have like three things in the product rule, I still use, the sign doesn't change, right? I think it does, right?
I think it stays the same.
Okay, then it stays the same.
I
I mean,
haven't really.
sorry?
I mean, I've never really done it with three products, but I guess it would be the same.
Okay, let's keep it the same. I mean, it doesn't really matter for our end result. So check on the signs, okay? Look, physicists are really bad with signs. Okay, I make signers all the time. Sometimes I'm like, wait a second, that should be a positive. That makes a big difference for the end result, but it's trivial, whatever. Okay, fine. Now I differentiate phi. Okay, what do I get? I get a prime, right? Oh, no, yeah, no, a stays the same, right? I already differentiated it. So I get ai phi prime, right? I'm going to do two derivatives on this thing. Actually, no, I should write this as phi double prime because this is just different. It's not actually pulling down another factor of phi. It's just differentiating this same thing again, just to signify that it doesn't really matter. E to the I phi. Okay, now I have one more thing I need to differentiate, right? This guy, that's it, and I'm done, the exponential. So the A stays the same, the I stays the same, the phi prime stays the same. From the exponential, I get a factor of I, and I get a factor of phi prime, and my phase stays the same. Yep, and that is it. That is d2 psi dx squared. And we're going to do some manipulation of this. Just a little bit, not a lot. Are we okay with those derivatives? Okay. So it's really not as bad as it looks when people write it out.
After all the previous integrals, it doesn't look bad at all.
No, yeah, integrals are kind of bad, but see, that's the thing. Integrals are really bad. They can get really bad. As you have, I don't know how in depth Gabe went with the contour integrals. I mean, those are hard. You need to really, did he go into the Laurent series and all of that kind of thing?
I mean, it was pretty clear.
Okay, all right, then that's good. You know, it's funny, Feynman hated contour integrals, hated them. So actually Feynman invented a trick and he never did a contour integral, which is so hilarious because you'll see in field theory that we derive something called the Feynman Propagator. And that propagator it has something that is a direct consequence of poles, of your integral hitting the poles. So, and he got that without even doing contour integrals. He did something called differentiating under the integral sign. He just ignored all of that stuff, which is so funny, but that's what Feynman did. He was not a mathy. He was very mathy, but he developed his own tricks. Okay, I'm going to pull out this e to the I phi, okay? That's an easy thing to do. So let's just write it up here. So d2 psi dx squared equals e to the I phi. I pull this thing out and I get a double prime. Pulled out, I get plus a prime I phi prime. I get a prime I phi prime plus ai phi double prime from this thing plus, so now this is going to become a minus because my two signs, the two i's give me a -1. This is phi prime squared, so I get plus a phi prime squared. Okay, so that's what I need in Schrodinger. Okay, and another thing I can do is I can combine these things, right? Right, so this gives me 2a prime I phi prime. Okay, so that's my final expression, and I think you're right, Rika, it should be a plus sign. That's the only way that makes sense. Okay, and now I can plug this into Schrodinger, right? So now I know what that thing is. I know what psi is, right? Psi is just a e to the I phi, okay? That's what psi is. Now I plug into star. I plug into Schrodinger. We'll call it star. So when you plug into star, what do you get? You just get e to the I phi, this whole thing, a double prime plus 2a prime I phi prime plus a I phi double prime minus a phi prime squared equals minus p squared over h bar squared a e to the I phi. I get rid of these things, right? I divide through by that, and I get my final expression for Schrodinger, a prime plus 2a prime I phi prime plus a I phi double prime minus a phi prime squared equals minus p squared over h bar squared a. Okay, and that is my final expression. Now what can I do with this? We'll discuss in a minute. This takes me back to sophomore year, struggling through Sakurai, trying to derive this because the professor did not really derive it. He just threw up the final expression. There's a garage sale happening across the street, so I'm kind of trying to get an idea of what they got. Are we good? Can I move on? Rika, Lizzie, was my calculus okay?
Yeah, I looked up
Yeah.
the product rule for more than 3, and that's right. You add all.
Okay, good. No, I think it's right. So that's the thing. That's the beauty of physics. This is a beautiful example. You don't have to, when I was doing this, you don't have to memorize anything. That's the first thing. Second, this is a good example. We're just working it out. Second of all, if you make a mistake, you'll figure it out at the end because I kind of know what I want to get. That's the awesome part. If we were biology students or chemistry students, we couldn't get away with that. We'd really have to memorize, it's important. Okay, let's move on. So I'm going to rewrite my final expression up top. Okay, and what we get is we get a double prime. This is just what we derived, so no big deal. I just want it up top. Okay, now this is kind of clunky and it's really, really hard to work with. I mean, I can't really do anything with this. However, I kind of remember a math professor saying once, and this is true, it's not like I vaguely remember. When you have a differential equation like this, and your intuition kind of should agree with this mathematically, now I'm not going to go so into it, obviously. You can split up this differential equation into real parts and imaginary parts. Okay, you can always do that with any differential equation, really any equation. So I see here that I have 2 imaginary terms and I have 3 real terms. So I can get 2 equations, right? Which is good. So let's do that. So I get a real equation or real part. We'll call this the real part equation. And this is just a double prime plus a phi prime squared p squared over h bar squared a, right? So that's the real parts. And now I have my imaginary part equation. Equation. And that is 2a prime I phi prime plus a I phi double prime equals 0. Okay? So now I have kind of 2 smaller things to work with, which is kind of nice. And another benefit of this, the other kind of benefit to this is I can kind of ignore one and work with the other, okay, which is what I'm going to do, because that's what makes it easy. So I'm going to focus on this one, the real part, okay? Turns out solving this part is really trivial. You really don't get anything interesting. So let's work with the real part. Let's call it star, and let's manipulate this a bit. And then we're going to use something, actually, now we use something called the Wkb approximation. Okay, now we need that. So what is the Wkb approximation? This is kind of like the Born approximation, right? In the Born approximation, we stretched out the waves a lot, and we had the waves come from a really far distance to our scattering target, right? That's what we did in the Born approximation, very loosely. Wkb approximation, what we do is we're going to let the amplitude vary very slowly. In other words, I'm going to make the amplitude really, really, really big on my waves, okay? And only focus on the phase. This is good in certain situations. So what does that mean mathematically? So what I do, let the amplitude vary very, very, very slowly. Okay? And what does this mean? This means that A double prime over A, this ratio of the amplitude is going to be much less than phi prime squared. That's really what this is telling me, just based on the terms I'm looking at. What this also means is that I can ignore A prime and A double prime, right? Higher order derivatives of A. Because if A is really small or really slow or really tiny, the amplitude is tiny or large, really large, I can ignore its higher order derivatives, right? Because this is just some constant. I've just made it vary really slowly. Okay, so this is what the Wkb approximation actually is. Now it sounds kind of silly, okay, great, but it turns out I can get a really beautiful form of my wave function thinking about the physics in this way. Okay, so let's apply this approximation to the real part. And some of you might already see it because it's already there. We just have a few steps. Okay, can I erase this? Okay. Okay, great. So what is WKB? I will just write it here again. It's just that A double prime over A is much less than phi prime squared. Okay, so let's do some magic with this. The imaginary solution, again, is not very interesting. You get something kind of trivial. So what do we get? So I can do some algebra. So I move A prime, double prime. I move this term over. Minus A. Okay. Oh, the beauty of algebra. You know what I tell people? I say, if only you learned algebra, you could practically learn everything. Really is nothing else to it. Okay, I move this thing over. I'm going to take out an A, and I'm going to kind of get rid of this negative sign. I take out the A, and I get rid of the negative sign, so this order is going to change. Well, I don't get rid of it. I get rid of the extra one. Okay, that's legal, right? It's like when you learn the rules of chess. I don't know if any of you like chess. I love chess. You know, you have to play by the rules. Same thing here. Is this legal or? I'll rely on Rika. She's my algebra checker. I'll say it in the camera now, even for the 6 people on YouTube. I'm not liable for any algebra errors. You are. There you go. I said it. Okay. And you can see this should be very, very suggestive. You should be going, oh no, I see what he's doing because I'm going to divide by A. WKB. So now I use WKB. This term goes to 0. Well, I'm not going to do it like that. Hold on. First of all, I need more space. So I'm gonna put this result up here. Up top. I'll erase this stuff. I mean, we really don't even need this. We kind of are done with this. Okay, so I have this. I'm going to do this in a better way because I don't want it to be, you'll see. Okay, so I have this. Okay, now I move this over. Yeah, it doesn't matter. Yeah, I didn't want to say this goes to 0 because this is just really, really small, right? It's much smaller than this. So now I use WKB in this form. It just makes more mathematical sense. Okay, now this term drops, right? Drops. That's what I get with WKB. Now I'm here. Okay? Good? Now I get rid of the -1. I divide by -1. Now I'm here. Okay, now we're in the golden zone. Whew. Nothing beats algebra at 6:30 in the morning, right? I shouldn't be talking because it's like 10 o'clock here, 10:30, so we got it lucky. Okay. Great. Now I can solve this. I'll solve it. I'll show you how to solve it. This is a differential equation that's very easy to solve, which any high schooler should be able to solve. You know, it's so funny. I was thinking of you guys. I was hearing this physics dude on YouTube, like doing an interview. And this is the line that stuck out to me. You guys will get a kick out of this. He said, God, why don't we teach those damn high schoolers Hermitian operators and just cut to the chase? I started cracking up. I said, that's what we're doing here on Saturday mornings. We just cut to the chase. Okay, let's do it. Let's solve this thing. Okay, great. So now I have phi prime squared equals p squared over h bar squared. Something really simple to work with. And now you should be kind of, your intuition should be ticking because I'm getting some kind of phase out of this. That's what I'm deriving. I'm deriving a new expression for the phase. Okay, that's what's really interesting here. So now what is this thing? First, let's just square root both sides. Okay, now what is phi prime? Phi prime is just d phi dx, right? So this just goes to d phi dx, right? And now I can separate the variables and integrate both sides, which is the favorite easy trick of solving these differential equations. I have two differentials. I'm going to separate them. So I get d phi equals p over h bar dx. Just moved it over. Now I've separated the variables. Now p is a function of x. Let's not forget that. Okay. It's implicit. Now I integrate both sides. The h bar pops out because it has no x dependence. So 1 over h bar p of x dx. Cool. This thing just gives me phi. And just gives me back whatever I was working with. I've derived a phase. I don't know what P of X is. So I derived this expression for the phase, the integral of P of X dx. Pretty cool. This is interesting. And of course, this can go into my wave function, right? Because remember, the most general wave function looks like this. So now I know something about phi. Kind of cool, kind of neat, really neat, actually. Why? This is like a velocity, right? This is like some kind of momentum. And you're integrating it. What's an integral? Let's just make something random and think about. First of all, I'll give you a second to copy that before I get to the punchline. Man, what's their names again? What are their names? Man, Wenzel really got it this time. Really hit the nail on the head with this. I don't know why people didn't think of this before Wenzel. Okay, so let me write this up top. Okay, this is why this is also called the phase integral approximation, for this reason. So now we've derived phi of x equals 1 over h bar integral p of x dx. Okay, fine. Okay. Now let's just say I have some random thing. It's doing all kinds of weird nonsense, okay? And this is oh wow, that is let's make it a little bit more, a little better than that. That's a little crazy. Here, it's doing like something like this. Whatever, I don't know. Okay, now this is some kind of P, right, of my wave function, right? Now, let's say I'm integrating here. If it's moving really, really fast, well, I don't know if this is how I want to do it. Yes, it is. If it's moving fast, right, the area under the curve is going to be small. It's going to be tinier because it's going to be there for a shorter period of time, right, versus when it's moving slow. So this is kind of a very interesting way to phrase this whole idea, right, of the phase. Right, that the phase is somehow, so this is just kind of what we're doing diagrammatically, that the phase is somehow linked to the velocity. And, if something's moving faster, the area under the curve is going to be less. It's going to be there for a less amount of time, okay? So this is interesting. So now let's see how this looks in the wave function. So let me rewrite my wave function. I'm sorry, you're going to get a weird normalization. C over square root P of X. You know how this stuff works. This is just a constant. This is when you do calculations, you'll say, thank you. He put the normalization in there. No one derives this. You just put it in. Okay. E to the I, plus or minus I over h bar, coming from this, integral P of X dx. And this is our famous, what you should remember from this class, Wkb equation. And I should put a little tilde over the equal sign because it is an approximation. It's not the actual exact wave function. Okay, we derived the phase. This is kind of cool too. You see an integral in the exponential. I wonder why. The path integral kind of looks like this. Ooh, I don't know. Okay, so this is it. Done. Drop my chalk. Now, you will see how this becomes very useful for solving very interesting problems. One problem this becomes very useful to solve in, Mansour wrote a paper about this, is tunneling. So Mansour, you're a very lucky guy. Actually, you're an unlucky guy because the whole mathematics of tunneling is a Wkb approximation. So you probably should have waited until we did this lecture, but it's okay. Okay, so I'm not going to do any problems with this because you have some in the homework. Gabe will go over them, and you can do them on your own. And what I want you to read about, though, there are a few things I want you to read about. One is George Gamow's alpha decay. So Gamow used this result to actually prove how alpha decay would work theoretically. You should read it. I have the derivation of what he did, but it's not too long, and you should read the story. 2, George Gamow was a great physicist. 2, I want you to read about the so-called Airy functions. Okay, very important. You know what those are. So those are the 2 things. And then if you want, read about tunneling. If you want, up to you. Okay, so these are the 3 things I would have covered, but I want to do this review of quantum and a little bit of classical, which is what I did for the Science Honor Society. Okay. Good? Was this derivation more clear than others?
It was the most clear derivation in this course.
Okay, good. I tried to go much slower, so. Good. I'm glad. Okay, so now let's take a little break. It is 10:24. We'll come back at 10:30. I'm going to go for about 45 minutes. I'm going to ask you a lot of questions. So what we're going to do a survey system in this chat where you answer yes or no. And I ask if you can have your camera on, have it on, because this lecture, so I'll give you my style. I'll give you more break time, don't worry. Here's my style. When I go into a room, Isha's not here today. There's usually 60 to 70 kids that show up, okay? And in a big class, I remember being in high school, you're like, oh, okay, I'm not going to get called on. What I would do is I'd go in and I'd cold call, okay? Because I want a discussion. So if you can have your camera on, that'd be nice. If not, that's okay, I guess. But we're going to do that lecture, okay? So take a break, come back at 10:30, and then we'll start. Okay, Bob, this was inspired by you, actually, from our discussion last week. Actually, I found the script for this talk I gave shortly after we discussed last week. So I was like, let me just do it this week because the topic's kind of light, so.
Thank you.
All right, this is the crash course. Jenna, was that better than before? I know you haven't taken calculus yet, so it's not easy to.
Yeah, I've over the past few weeks I've been like doing Khan Academy, so I knew like the product rule and the chain rule stuff, but I don't know like any.
You want to know
answer
the
rules.
best source to learn calculus? There's only there is one source that is so good. This is how I learned it. MIT OpenCourseWare.
Oh yeah, I've seen some of their videos.
Yeah, and the
Yeah,
best
yeah.
part about calculus, they have their whole calculus series on edX, EDX. So you can literally save your progress, do the same problems the MIT kids did, it is so amazing. It's incredible. I would just work through that whole class. And the best part is you can save your progress as you go, like Khan Academy. And it's all on edX. In fact, I think their quantum mechanics class is on edX too. I might be mistaken. And it's actually taught by Barton Zweibach, who wrote this book,
Cool.
who wrote a first course in string theory. This was by Barton Zweibach. This book is what I'm using now. So I'm in string theory now, and the book we're using is so difficult. So I said, let me buy the undergraduate book, Lifesaver. So yeah. edX, highly recommend. It's just amazing what people can learn, right? In today's day and age, you can become a quantum field theorist in your living room. I mean, almost, not totally, because you need to talk to academics. That's the thing. That's hard to do. Otherwise, your ideas are probably crackpot. You don't really know what's going on. Okay, we'll give everyone another minute. Okay, let's begin. So this is going to be not very mathematical, but it's just to kind of make sure we're all on the same page with the conceptual basis. And also get us starting to think about, and I'm going to, so I'm going to show you something called a Lagrangian. I'm going to do a lecture for you guys in the winter on Lagrangian mechanics, and we're going to go very in depth. I'm going to derive it because it's so important. But I'm just going to show it to you very, very hand wavy today. Yeah, so let's get started. So what are we going to start with? We're going to start with our favorite beast. Can someone guess what I'm going to say? There's only one thing that we could start with. Starts with an H. Oh no, don't make me say it. Someone should know.
Did you ask something?
Oh yeah, I did. I said, what is the only plausible thing we can start with for this?
For what?
For what we're about to do. It starts with an H. It's the physicist's favorite thing.
The hydrogen atom?
Almost the harmonic oscillator, right?
Oh.
That's the only thing we can start. I mean, if you want to start with hydrogen, we can. We'll be here for an extra hour, but okay, so let's start classically. Let's think classically. So I have an oscillator. I've shown you this before. This is review. It's got some mass. I attach a spring to it, and I let it go at some distance. Oh shit, sorry. Final and initial. Okay. And I ask you guys, all you brilliant AP Physics scholars, what is going on here? What are the forces of the system? And you say, oh, that's easy. We just have to solve F equals ma. And I go, yes, you're right. That is all you have to do. So F equals what here? You're pulling the spring out, right? The spring has some force, the spring constant, right? And you're pulling it out at some distance. And when you let it goes in this direction, goes in the negative direction, right? So all the forces here are minus, because it's going backwards. It's recoiling and then jiggling. K, the spring constant, right? Tells me how strong my spring is. X, okay, the distance. So this is my solution to F equals ma. This is what you'll do in high school, right? Or even in freshman physics. You just write down Newton's equation and you solve it. Now, I really want you to stop me if you have questions, because this is really, really the conceptual foundation. So if this is unclear, you have to let me know, okay? Great. So what does F equal, guys? F equals ma, right? And in physicist notation, this is mx double dot, right? Two derivatives from position. So mx double dot equals minus kx. Okay? I haven't done really anything here. Too difficult. Now, we know from springs and from high school physics that omega, we'll call this omega naught. Omega naught is the frequency, k over m, square root. What is the frequency? The frequency is how much it's going to go back and forth when you let it go. I did not because this is what we call the natural frequency. This is if you just let it go at this point without pulling it out. What would it naturally oscillate at? Okay, now I'm going to divide through by m. Okay, I just divided through by m. This goes away. Okay, I move this thing over. Plus k over m x equals 0. Oh, this is just omega naught squared, right? K over m. So I get my final beautiful equation, x double dot plus omega naught squared x equals 0. Okay. Okay, this is great. Awesome, wonderful. I now have what we call in physics an equation of motion, right? So you have all seen equations of motion. The kinematic equations are equations of motion, right? In kinematics, right? V equals d over t. That's an equation of motion, right? V equals d over t. We had we used to joke that we were V bar. We used to joke that we were a gang. We were called the V bars in high school. I don't know where that came from, but right? And then you can derive more equations of motion, right? That means that t equals d over v, right? That means that d equals v times t, right? And now I have equations of motion to work with, right? And I have an equation of motion. So in some sense, this tells me everything about the harmonic oscillator, classically, right? Like this is it. This is all I need to know. Yeah? EQ of motion. This is a differential equation. What are the solutions to this? They're sines and cosines, right? That's what will solve this thing. So the solutions to this are sines, so solutions are sines, sine and cosines. What are sines and cosines? They're oscillations, they're waves. So it's so cool because this system that's macro, we can describe it as oscillations mathematically. That's why this is called the harmonic oscillator. It's because that jiggling of the spring can be modeled by sines and cosines. It's an approximation, right? That's what we do in physics. Basically, everything in physics we're solving are these approximations to modeling nature. Kind of cool. Okay, does this all make sense? Okay, now I'm going to get this same equation in a totally different method. Totally different. Can I erase all of this? This is just basic. We did this. Okay, so now I have the equation of motion. Right? This is really the most important thing. So equation of motion. And again, solutions are oscillations. Solutions are sines and cosines. Okay, excellent. Now, we're going to use another method called the Lagrangian. And this is called Lagrangian mechanics. And basically it was invented by a guy named Lagrange, and it turns out to be a super powerful tool. And I'm going to show you how I can get the same equation in motion using the Lagrangian. Now, I'm going to derive, let's just go slow. So what is a Lagrangian? Script L. It's a function, not really, but it's a function that goes kinetic energy T. Yes, we call the kinetic energy T. Everyone always says, why is it T? I don't know. That's what they made up. T minus U, potential. Okay, this is what I call my Lagrangian. So this is great because now you're saying, oh, Kyle, from energies, you can give me equations of motion. Energies are really easy to write down. There's not that many options. Now we know what a Lagrangian is. How did I derive the Lagrangian? You don't derive the Lagrangian. You just posit it as a mathematical thing. Now it turns out when we solve these equations called the Euler-Lagrange equations, Euler-Lagrange equations, we can derive this equation of motion. Now, I have to tell you, the derivation, and I'm actually going to say this with a straight face, the derivation of the Euler-Lagrange equations is the single most important thing any physicist learns. I said it. There's no other derivation that's more important to understand than the derivation of these equations. I'm not going to derive them now. I'm going to derive them in the winter. But the way you derive these equations is you do this process. You do this thing called minimizing the action. Turns out, minimizing the action, you can derive any equation in physics. You can derive the Maxwell equations for electricity and magnetism by minimizing an action. You can derive the Einstein equations. You can derive the standard model. Okay? In fact, the whole standard model is a Lagrangian. That's what the standard model is. Okay, that's how powerful this is. So this, I mean, I told you I can't derive a Lagrangian. That's true. It's just an object. I can derive these. And that derivation is super, super important. But I'm not going to do it now, so just take the equations as face value. So here's what they look like. They go del Lagrangian, del x minus d dt, full derivative, del L, del x dot equals 0. This might be the most important equation in physics. Now, you want to know a really funny story? When I write this at the high school, everyone goes, because they see curly D's. So I didn't get that reaction here because you all know what this stuff is, partials. Another really funny story. For my 16th birthday, my friends bought me a birthday cake, and guess what they put on it? They put the Euler-Lagrange equations. So when I say they're important, they have personal meaning. Because when I turned 16, I looked at my cake. And, you know, most people get a nice little message, you know, and they go, oh, that's cute. Yeah, I got these and I started tearing up. I mean, a tear flowed down. It was so beautiful. And I felt so bad for the person that had to pipe.
That's a beautiful story.
Okay, excellent. Let's solve this. Let's see if we get this back. Let's do the first piece. So del L. Oh, shoot. We have to write down the Lagrangian. We don't have Lagrangian yet. What is my Lagrangian? My kinetic energy is 1/2 mx dot squared, right? X dot is v, right? So 1/2 mv squared, velocity, x dot, minus the potential. What is the potential for the spring? It's 1/2 kx squared, right? That's the potential energy for the spring. If I was doing a projectile, it would be like mgy or something, right? It would depend on the system. Okay, I have my Lagrangian. Now in quantum field theory, we'll have a Lagrangian. It's not going to look like this, but we'll have a Lagrangian. It's going to need to incorporate special relativity and other things. Which, by the way, we're going to have to learn special relativity. I'm sorry, but it's too important. Beautiful. Now let's solve. So what is the partial derivative del L del X? Can someone tell me? I'm going to cold call. Not on you, Jenna. You're still learning calculus, so don't worry. You're still learning. You're still learning. But I'm going to cold call on everyone else. What is del L del X? Let's solve the Euler-Lagrange equations. Let's do the first term.
Mx divided by, just mx dot.
Mx? So this is velocity dependent, right? This has no x dependence, right? So for
Yeah, x dot I meant, like velocity.
no, but this is del L del X, right? Not x dot.
Oh,
So this term is not gonna matter, right? It's a partial derivative. Is that
I
okay?
got it now. Yeah.
Yeah, so this term is like a constant. It has no x dependence. All I care about is this term. So then what do you get, Ola? All I'm differentiating is this.
Minus kx.
Exactly, minus kx. Now let's do del L del X dot. Okay. Rika, what is del L del X dot?
mx dot.
Mx dot, exactly. Okay, now we need to take the time derivative of this thing, right? So what is d dt of del L del X dot? That's what we need, which is really d dt of mx dot. What is that? It's really easy. I'm not trying to trick you. Mansoor, what do you think?
Maybe
It's okay, just take a guess. It's fine.
so maybe mx dot equals d.
Well, I'm differentiating this guy, right? So I'm just going to get mx double dot, right? It's one more time derivative. That's it. Yeah?
Yeah.
Okay, good. Whoa, okay, let's plug in. Del L del X is, this should be a K, what am I writing here? God. Oh no, I'm right. Like, what am I writing here? Del L del X minus Kx minus this piece, mx double dot, equals 0. Wait a second. This is exactly what we derived. This is just mx double dot plus kx equals 0, which is just x double dot plus omega naught squared x equals 0. There you go. So basically, and this is where people go, whoa, because this is kind of like you would never, this intuitively would not really, you would not see the connection. I don't know how Lagrange figured this out. So this is the basics of Lagrangian mechanics. Obviously, we're going to derive this because this is so important to quantum field theory and just physics. Like this is so important to physics. You know, that's how you know if someone knows physics, because if you ask them what the most important thing about physics is, if they say black holes and string theory, they don't know physics. If they say Euler-Lagrange, they're a physics major, because this is it. Like this is everything. I minimize the action, quote unquote, like 500,000 times. Like that's what you do. That is physics. Because what do you need in physics to do anything? You need an equation of motion, right? I mean, that's the heart of it. It's really that simple. It's not that, I mean, yeah, you can make the system as complicated as you want. At the end of the day, I just need an equation of motion, right? Okay, so we have a classical kind of idea now of all of this. Like this is classical now. This is kind of nice. So any questions about this? Okay. So this is all classical. Classical harmonic oscillator. And from this, we get oscillatory solutions. We get all of that kind of stuff, positions, momentums, velocities. Okay, can I erase? Okay. Wonderful. So let's make the classical checklist. Classical simple harmonic oscillator, SHO. You have an equation of motion. You have a Lagrangian. What was it? Oh, yeah. Okay, that's for the oscillator. And that's it. That's all you need. Now, we will learn what an action is and all that kind of thing. We'll do all of that. Let me see if I can find this in my... Okay, this is my paper that I'm working on now. The very first equation is an action. Okay, and from that action, you write down a Lagrangian. So that's, and when I tell you that this is it, unfortunately, I'm being honest, but don't worry, there's a lot more detail to it. It's not quite it. Okay. Okay, now we get to the conceptual basis for quantum mechanics. Okay, so I like to motivate quantum mechanics with the oscillator. We already know about Stern-Gerlach and probabilities and all of that, so we're okay with all that. That's like stuff you hear all the time. But actually, the systems that we're solving, you might have noticed, like our notions of probability become less important, right? Once we actually start to do quantum mechanics, right? Like I haven't really brought up a lot of probability since. Why is that? Because in our system, what are we doing? We're making a measurement. So yeah, we kind of have to deal with probabilities like in retrospect, but not really after we get our energies or we get our angular momentums, because we know what they are. It's not like Lizzie is looking at her energies because she did a paper on energies for the driven damped harmonic oscillator, it's not like she's looking at them and going, oh man, I don't know if it's really 2 or 3. No, she knows if it's 2 or 3. Okay, like that's, otherwise this would make no sense. So yeah, we have a problem with probabilities, but it's not as bad as people think, right? Like everyone loves to, if you're at a dinner party, someone will come up to you, they'll be like, Serafina, have you heard about Schrodinger's cat, man? It's like so far out, like is it dead or alive? And I have to ruin it for them as the physics person in the room and say, well, we opened the box. Okay, so we do know. Now before I can't really answer it, but you know, the good news is we actually get to open it. Okay, we're not sort of sitting there looking at the clouds. Okay. Okay, let's talk about quantum mechanics. So here's where my survey questions come in. Okay, quantum mechanics, how should we start this? We somehow have a wave-like thing built into our program, right? Because as we've seen, psi is modeled, so our wave function, the state, describes the particle, right? This is the most important key object if you're learning quantum mechanics, this little thing. Psi is the particle's state. The state is in this ket. The ket is a vector, right? And this ket tells me all about the state psi. Now, please stop me if you have conceptual questions, because this is super important. And, you know, we learned about in states, right, versus out states, right? We learned that these are Hermitian conjugates of one another. We learned, we did so much stuff with this, right? So, but if you're showing this to someone that doesn't know quantum mechanics, you just say this represents some state, right? Now, psi can be written as plane waves, very vaguely. Guys, what is this equal to from trigonometry? A set of sines and cosines, right? You can rewrite this as a set of sines and cosines. So it's literally something oscillatory. Okay, so we're starting to see the connections. Okay, so we're going to need a quantum SHO checklist. So what are we doing? We have states. They behave like waves. But somehow we have this idea of discretization that I keep bringing up over and over again, right? Somehow we take a classical system like the harmonic oscillator, we quantize it, and we get energies, for example, at discrete values, integer values, right? What is the process of quantizing, though? What is that process? That's the key to understand. What is the process of quantization? So let's think about it. My first question. In classical mechanics, we worked with a Lagrangian, T minus U. What seems to be the analog of the Lagrangian in quantum mechanics? Think about that for a second. Now, what you should, let's talk about something else for a minute though. This is what I call the quantum mechanical program. Let's do this first. Step one, take all your degrees of freedom, position, momentum, velocity, forget velocity, position, momentum, because this is really velocity, and promote them to operators. Okay, that's what we do. This is the process of quantization. You take your degrees of freedom, you make them operators now on states. Right, so these operators act on states, right? Or Hermitian conjugates of the state, right? In and out states. Right, we have objects like this. We have all kinds of things, right, that we can create. We have Heisenberg operators, we have angular momentum operators, we have creation and annihilation operator, raising and lowering operators. Second part of the program, have them satisfy commutation relations. Okay? So they must satisfy commutation relations. And usually for the public lecture, I go much slower, but you guys know a lot of quantum mechanics, so I don't have to. Commutation relations. As we know, this does not equal 0, equals I h bar, or I. We made h bar equal to 1. Okay. This is the algorithm. Why do we do all of this? Well, we know probabilities and this and that and blah, 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 blah. There's a lot of things that go into why this has to be this way. Uncertainty, right? The fact that we want eigenvalues and the whole mathematical structure. I mean, this algorithm is simple, but the motivation for it is very complex, which we've gone through all of the reasons why we have this algorithm and why it works. Okay, now let's go back to my original question. So let's do the quantum harmonic oscillator, right? We know that we're dealing with states now. Guys, when I say quantum harmonic oscillator, it's not actually like exactly like the classical harmonic oscillator, right? There's no like box I'm pulling and letting it go. It's less intuitive. Okay, guys, so this is what I want to know. What is the analog? What seems to be the analog in quantum mechanics to our Lagrangian from classical mechanics? Hint, it's a big part of the Schrodinger equation that we're trying to solve. So in quantum mechanics, our equation of motion is this. Right? This is the equation of motion. This is acting on psi. It's giving me back some energy eigenvalue. This is F equals ma. So I should write that down. Here we have F equals ma. Here we have h hat psi equals e hat psi. That's why they don't start you with quantum mechanics in freshman physics. Okay, cool. Now we'll actually let you answer my question. So what is the analog to the Lagrangian in quantum mechanics? What seems to be the analog? Lizzie, what do you think? It can only be two options. Maybe she's not there.
She just showed that her microphone isn't working.
Oh, that's fine. Okay, another hint. What is, okay, here's another hint. What is an object in Schrodinger that seems to deal with energies? Like what is an object in Schrodinger that seems to, yes, the Hamiltonian, exactly. So that is the analog of the Lagrangian. Turns out there's another kind of mechanics called Hamiltonian mechanics, which we will also learn very briefly. You solve the Hamiltonian equations, and you can also get this thing out. So there's another formulation. The Hamiltonian is equal to T plus U, the total energy. Yeah, okay. And you kind of use what's more convenient. In particle physics, Lagrangians are way more convenient. And Lagrangians are almost necessary. And you'll learn why. They're necessary because they impose Lorentz invariance, which you'll learn what that is and why it's so important. Okay, so we have an analog. The Hamiltonian is kind of like a Lagrangian, right? We write down our energies and we solve. That's it. It's the same kind of idea. So now, what is the Hamiltonian for the quantum harmonic oscillator? It's just 1/2 mx dot squared plus 1/2 m squared omega squared x squared, right? This is what we wrote. I only wrote down the potential. piece. But this is basically, I mean, this is the analog of, what is it? Yeah. Okay, this is the analog of this. Okay, so this is my Hamiltonian. So we can add that to the checklist. 1/2 looks very similar to classical physics. Now, what do we get when we solve this thing? What do we get? We get energy eigenvalues, right? And energy eigenstates. What are those energy eigenvalues? E sub n. Now we're dealing with multiples of energy, right? That comes from quantization, right? Equals, what did we get? We got 1/2 h bar omega plus n, right? That's what we derived, right? I'll write it bigger. En equals 1/2 h bar omega plus n. Now, energy is not a continuous thing. In the quantum world, energy can only be certain values. 1, 2, 3, 4, 5, blah, 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 right? Okay, this is like super, super important. This is what quantum mechanics does. It discretizes energies. Hydrogen atom energies are discretized. Infinite square well energies are discretized. Scattering states are just everything we've looked at. This also comes directly from this. E equals h bar omega, which is something you've all seen in high school physics. This is just the energy for a wave. Or you probably saw h, not h bar, but. So this is all kind of nice. It's all so connected, such a beautiful way. You know, when people say quantum mechanics is so hard, that's what people love to say. It's because they really don't know classical mechanics. If they knew classical mechanics, quantum mechanics is kind of like, it's weird, but it's same structure. The structure is the same. And when people say quantum field theory is hard, it's because they don't know quantum mechanics. It's the same kind of thing. You have to have the foundation in physics. It's like a big ladder in physics. Okay, wonderful. So we kind of have our quantum mechanical algorithm done. Okay, now what? This is the name of the game. Any questions so far? Anything at all? Okay. Now, last 5 minutes. Actually, I'm over time, but that's because I'm taking Gabe's time. What time is it? 11:06. I'll go for 5 more minutes. Now, special edition for you guys. Where are we going to field theory? Like what is the next step? Let's just talk about that briefly because this will motivate the path integral. So on to QFT. What is QFT? Deep breath. Okay, gets exciting. QFT is super weird, okay, in this way. I have something called a field. Okay, first of all, what is a classical field? That's probably what we should start with. We should always start classical. A classical field you've encountered. What are some classical fields? You have the E field, electric field, right? You have the gravitational field, phi, when I teach you, for those of you that make it through QFT, when I have to teach you a little GR, you'll be learning with these gravitational fields, and you'll be dealing with electric fields. What's a field? It's some object that's labeled at each point in space, right? It's just labeled at each point in space. So I have some electric field. It's labeled at each point in space. And at each point in space, I give my field a value of electric strength, field strength, right? Or I give it a value in gravity of the gravitational strength, right? The field strength at that point. That's all it is. So field is not a very complicated object. Okay, it's not very complicated, and you have to deal with them all the time. In fact, electricity and magnetism and general relativity are called classical field theories. Okay. Okay, fine. This makes sense. Okay, and when you solve the Einstein equation, you're solving for a classical field theory. So what's a quantum field? So the most basic quantum field we call phi. It's a function of x and t. This is what we call a scalar. Wow, we're kind of getting into QFT, but I'm just motivating it. I'm not really going to do much with this, obviously. We don't have the machinery. This is called a scalar field. Scalar being a scalar particle is a boson. A boson is a spin zero particle. Anyone know a very famous boson that they discovered?
Higgs?
Sorry?
Like Higgs boson?
The Higgs boson.
Higgs, yeah.
Higgs boson, exactly. So it turns out the Higgs boson is the only fundamental particle we know of that is scalar. Okay, that is spin zero. And actually Higgs fields are scalar fields, which we'll see like at the end of next term, because there's very weird things that happen with the Higgs mechanism. Okay, I have a quantum field, and at each point in space-time, I said space-time, we're not at space-time yet. So ignore this T. You see the T comes from special relativity. So ignore the T for now. Don't worry about the T. See, I said space-time, it slipped. At each point in space, we don't know what space-time is yet. At each point in space, I have some particle or I have some label. I have a boson. And each boson is modeled by a harmonic oscillator. And they're all linked to one another. Okay, so let's just say I have a free field. This is a free scalar field. What does that mean? There's no interactions in this scalar field, right? All the particles are free. And all of them are modeled by little harmonic oscillators. They're all kind of connected to one another because they're all influenced by one another in the field. Oh, this is kind of interesting. And the more particles I add, the more harmonic oscillators I get. Right? So that's why we say quantum field theory is a theory of infinite harmonic oscillators. Now, obviously, I have no interaction here. I have nothing interesting going on here. Right? I just have a free scalar field with a bunch of things kind of like lying around. Nothing's bouncing into, that's where it gets complicated. That's what we're going to have to learn how to deal with. Okay, fine. You want to know something funny? So when I teach you quantum field theory, I'm going to recommend to you like 100,000 textbooks that you're going to have to look at. You're just going to, or you're not going to know what's going on. There's PDFs of all of them. This one I'll recommend to you is by Tony Z. It's called Quantum Field Theory in a Nutshell. It's a complicated book. They're all complicated. They're all for by experts. However, this one is what I recommend to you if you're totally lost in math, because he makes it very conceptual. He doesn't do a lot of calculations. And in chapter 1, he writes, you guys are going to laugh at this now. Chapter 1, Motivation and Foundation. Section 1.4, from mattress to field. So his analogy is that a quantum field is like a big mattress, and all the springs of the mattress are all attached to one another, and they're all jiggling and oscillating, and as if you sit on one end of the mattress, you give an interaction, right? You move the spring, or, so there you go. So all we're trying to do in field theory is solve for the mattress. Okay, and in field theory, we're going to have a Lagrangian, which will look like this. Right, this will be the free Lagrangian, no interaction here. This is what we'll figure out. It has loosely to do with energies, doesn't really have to do with energies, right? But we'll see why we construct it in this way. We need like Lorentz invariance, we need other things. And that's it. And then these raising and lowering operators, which I should put in the checklist, right? So we had A plus and A minus that took me up and down the ladder of energy eigenstates. In field theory, they create and destroy particles. They're called creation and annihilation operators. So let's say I have this thing called the vacuum state. So this is a state with nothing in it. Turns out the vacuum actually is not empty. It actually does have things in it, but we're going to ignore that. If I have a creation operator, A dagger, which we'll see what that means, acting on the vacuum, I actually get back a particle with momentum K. If I have the annihilation operator acting on the vacuum, which is just A hat, I just get back the vacuum. I get back nothing. So now we have another direct analog to quantum mechanics. Instead of going up and down energy eigenstates, we're getting particles, creating or destroying particles. Okay, so hopefully this whole program in 20 minutes really gives you the broad brushstrokes. It is very skeletal, okay? Obviously this is going to take us a lot of thinking, and we're going to need to know special relativity. Okay, folks, any questions? Okay, I did not go too much over, so you guys have a break today from problem sets. You have a problem set that was due today. Send it to me next week with the other one. Give you an extra week. There's 2 of them because I know you guys like to see what Gabe did, and which is fine. That's good. It means you're learning how to calculate, which is fine with me. I don't care. And the workload will be lighter in terms of, actually it won't. I need you to do problems for the path integral. Okay, any questions? Okay, excellent. All right, well, take care. I will linger around if you have more questions, because I know Gabe was supposed to go till 12. So if you have anything, let me know. If not, you're free to go. This means that, yes, thank you. Hopefully your mic gets better. And this means that tomorrow I'm going to shorten my session. I'm only going to go from 9 to 9:30 tomorrow, because I'll be here today till 12. Not like anyone comes on Sunday. It's just me and Bob every Sunday morning, just saying. But that's fine. We enjoy it. So, okay, take care. I'll be here though. So.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Where did my camera go? So Bob, I hope that was a little, oh, I think he left, okay. Stop record.